Okay, calculus friends. These are actually, they're not difficult. The problem here is being able to visualize. Okay? So, volumes of solids with known cross sections. So you're going to be given an area in between two curves, just like we were yesterday. And we're going to be asked to find the volume of a three-dimensional figure where we know what shape we are trying to create with each of those cross sections. Okay, so imagine, if you will, a field. I'm going to draw this in 3 dimensions. So here we have an x and a y plane, right? That is 3-dimensional. So here's your vertical plane, right? This is your z, and this is your y maybe, and this is your x. Okay, so no, we don't ever deal with the z plane, right? The 3rd dimension. We only deal with it being flat. So imagine a sideways parabola, right? So this is a sideways parabola, and we want to draw squares. We want to build something that has the base shape of a sideways parabola, right? A base shape of a sideways parabola, but we want all of the things on this to be squares, right? What do we know about a square? The height is the same as the base, right? The height is the same as the base. So the base of our square is going to come from this. This length here is going to be the base of our square in between our two parabolas. And from that, we're going to draw a square, right, vertically, because it's volume. Okay, and if we go down some more, we're going to draw another square with this as its height, right? So we're drawing squares, and as you get a bigger and bigger distance in between your two things here, we get larger and larger and larger squares. So we end up with a 3-dimensional shape, right, where the height of your shape is the length, right? The height, let me change colors. The height of your shape, this is the height of your shape, is the same as the base of your shape, right? And the base we're going to be calculating and multiplying by this other thing. Okay, so it's 3-dimensional shapes with a geometrical base. Okay, now that probably doesn't help at all, but maybe it does. I don't even know. Okay, so the math says, right? So these are all examples. This is an example of, looks like a square base, right? We have a triangular area at the bottom, and we want square cross sections. This one we have a triangular base, and we have semicircular cross sections. So all of your slices, if this were, is it cake? Is it cake? Okay, so if we had this and you chopped the cake, every one of your slices would be a semicircle. Okay, for this one, every slice would be a square, right? For this one, every slice would be a square. This one, every slice would be a semicircle. So as you're chopping your cake vertically, what are the shapes of your cake, the cross sections that we're making? Maybe we'll actually do this, and I'll make some cake, and we'll do some cross sections. But yes, remember, this is volume. Volume is the accumulation of area. So the volume of our cross section is the integral of the area of your shape, okay, with respect to x. Okay, so it's an integral. Volume is an accumulation of areas. Accumulation is the integral, right? So we're adding up all of these different areas, and we're getting the volume of this. So if it's respect to the x-axis, then of course x is our variable. And if it's respect to the y-axis, then y is your variable. Okay, so we'll see how this works here on the next page with many, many examples. Okay, and we'll use our calculator to help us find that actual volume. Okay, but the words are cross sections. Okay, that's how you know this is what we're going to be doing, is it says cross sections. So our problem says set up an integral to find the volume. It doesn't actually want us to find it. It just says set up integrals. Needed to find the volume, right? We can use our calculator and actually do it. That's not a bad thing to do. So maybe we'll do that with some of these also. Whose base is the area bounded by the graph of y equals x squared and negative 2x plus 3. Okay, so our base is this shape that's bound by our two graphs. So we have y equals x squared. Hopefully you know exactly how to graph y equals x squared. Hopefully. I'm going to make mine a little bit. My y and my x are not going to have the same units on it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 0, 0 is my origin. Of course, I have 0, 0. So I'm graphing y equals x squared to begin with. 0, 0, if I go 1 over, that's 1 up, 2 over, 4 up, because the y is the square of the x. I go left 1, up 1, left 2, up 4, left 3, up 9, right? Because 3 squared is 9. So here is my parabola. Y equals x squared. And my next equation is a linear equation, negative 2x plus 3. So that one has a y-intercept at positive 3 and a negative 2 slope. So down 2, 1 right, down 2, 1 right, up 2, 1 left, up 2, 1 left, up 2, 1 left. Okay, one reason why I graph these is so I can see the bounds. Right, where they intersect is going to be my upper and lower bounds. Okay, these happen to be nice and pretty numbers. So this is the base shape, right? So I am making this the base of all of my shapes. That's where I'm going to build, right? Consider this to be an island in the middle of the ocean or just off the coast of something. And we have it as this shape. And we're going to build structures on it. It looks like our first structure is rectangles with heights of 4. Okay, so we're going to build rectangles with heights of 4 all along this island. Okay? So for a rectangle, the area of a rectangle is base times height. Okay, so that's the area formula that we're going to use. We're going to be taking the integral of the rectangles, adding them all up. Rectangle is base times height. Okay, what is the height of my rectangles?
4.
Always 4. It says that my height is always 4. And what is my base length? So the base of the rectangle is going to come from this, right? This is the base of my rectangle. However far it is between the blue line and the red line, that's the base of my rectangle. And the height is going to be 4. So how do I calculate that length from the blue line to the red line? And this is what we went over yesterday. That's the top function, which was negative 2x plus 3, the y value there, minus the y value of the function below it. Okay, so this is my base. That's the length between, or the distance between my blue line and my red line. Right? It's the y value from the blue minus the y value from the red. So let's look at a very specific rectangle, the rectangle when x is negative 1. Okay, so what is the base of my rectangle when x is negative 1? This has a y value of 1, 2, 3, 4, 5. And I can also plug negative 1 into my equation. Negative 2 times negative 1 plus 3, well, that's 5. And this one on the red is negative 1 and 1. So what's the length of the base of my rectangle when x equals negative 1? Hopefully you can do 5 minus 1 in your head and come up with 4. Right? The base, the distance in between your blue line and your red line is going to be 4. So what's the area of the rectangle that I would build at x equals negative 1? 4 times 4 is 16. Okay, and I'm going to do that for all of these at x equals 0, at x equals negative 0.25. At every single one of these distances, I'm going to build a rectangle. So what I'm doing is I'm adding up all of those. So that is the integral. Right? Volume is the integral of. What is my left bound? Where do these graphs intersect on the left side? At negative 3. And where do they intersect on the right side? At positive 1. Right? So those two bounds, the lower bound and the upper bound, are the intersection points of your graphs. Now, if we didn't know what they were, you could always set your two equations equal to each other and solve. Okay, in fact, that's what we're going to do most of the time, is set our two equations equal to each other and solve. So, of course, if we do this, that gives us a quadratic when we bring the minus 2x plus 3 to the same side as x squared to keep x squared positive. And we would, of course, factor our quadratic to x plus 3 and x minus 1. And we could figure out that those two equations are equal when x equals negative 3 and x equals positive 1. Okay, so maybe the graph is really, really hard to visualize. So you set your equations equal and you solve that, and that gives you your lower and your upper bound. In this case, negative 3 and positive 1. Okay. So the area of my rectangle is the base of my rectangle times the height of my rectangle. And how do we calculate the base? That was this right here, right? The base was the distance in between your two graphs. So the base of my rectangle is found by doing negative 2x plus 3 minus x squared. Right? That's the distance in between your two curves. That's what we were doing yesterday, is we were finding the area by taking the integral of the distance in between your two curves. Times, what is the height? The height is always 4, right? A constant height of 4. And because we're doing it with respect to x, we're going to have dx as our, as whatever that thing is called. So this is going to be our formula, right? It doesn't say to evaluate it, but we could simply by plugging it into our calculator, and it would tell us what that volume is. Okay, let's check and move to our semicircles. Okay, so the graph doesn't change, only the pictures change. Right? So I'm going to draw the graph again and see if we can do this better. Okay, there's the graph. Now imagine, if you will, building a semicircle on each of these heights. So if I'm going to pick this one, for instance. Okay, now I'm going to draw it flat, but imagine it's coming out of the screen. So it's a semicircle like that, right? But it's standing up vertically. The semicircle is a vertical thing compared to the base. Right, so we're going to make a whole bunch of semicircles. Right, so this is going to be a semicircle based upon the distance in between my two graphs. Right, so just think about, what is the area formula for a semicircle? 1/2 of pi radius squared. Okay, so as long as you know your formulas for your areas, we can take the integral based upon these different areas. But notice the radius. How do we calculate the radius for our semicircles? Is the radius the same as the distance in between your graphs? No, it's not. It's half. The radius in this case is half of the distance in between your graphs. So half of negative 2x plus 3 minus x squared. Okay, so if we're taking a semicircle, the radius is not the entire length, right? Because if it was, then our semicircle would not actually be built upon our island anymore. Half of it would be built out above the sea, right? Which is an amazing idea to have a deck that's over the water, right? You pay a lot of money in Tahiti for those kind of accommodations. But here, we're building strictly on the land, so we have to find the middle of our island and then build the semicircle from there. So our radius changes, right? But it still involves your formula of the top equation minus the bottom equation. That's how we find the distance in between our two curves, is we do the top equation minus the bottom equation. So this one's formula would look like the integral from negative 3 to 1, right? That part doesn't change. 1/2 of pi, right? Those are constants. So in essence, we can pull that outside of your integral if you want, because this is a constant. 1/2 of pi is never going to change. So you can put it out front if you want to, and it's still perfectly correct. Now my radius is changing, right? The radius is, like I said before, half of the distance in between my curves. Okay, and I'm writing it like this because it's the top equation minus the bottom equation. Okay, that's my radius. And what am I doing to my radius for my area? I am squaring it. Right? And then I don't have anything else, so dx is going to be how we finish off our integral. Okay, now we would do this calculation completely in the calculator. I would not want you to do this and tighter. It would be not pretty. It would be doable. You all are smart enough, but it would not be pretty to do. Okay, here's another one. Set up the integrals needed to find the volume of the solid whose base is the area bounded by this circle. Okay, what's the radius of my circle? The radius is 3. X squared plus y squared equals r squared. So this has a radius of 3. Okay, so we're going to have equilateral triangles, right? Pretty small ones to begin with, but then as we get a wider base, then our triangles get even bigger. And so we get to the middle, and that's going to be the biggest equilateral triangle that we're going to have. Okay, so I know this is not easy to visualize. Think about the mountain range going around a circular island with a mountain range going right through the middle. Maybe, I don't know. I like islands. They're fun to be on. Tropical and nice. Anyway, so think about your how are we going to get the length of our base, right? Since this is the formula, the side, right, the whole entire thing is the side of my equilateral triangle. So how am I going to calculate that distance? Right? That's what we have to think about, because it's the integral from negative 3 to positive 3, right? That's my left bound and my right bound of what? A circle? No, of a equilateral triangle. So this is going to be the area formula for our equilateral triangle, right? And we have to replace S, right? That's in essence what we're doing, is we have to figure out how in the world are we going to represent the side of this equilateral triangle as a mathematical equation based upon our circle. That's what we got to figure out, right? That's the part that needs some thought. dx. Okay, we've been doing some thinking off camera here. If I chop my circle in half, then I know half of my side length. And half of my side length is the y value of my semicircle. So I solve this equation for y, and I get y equals 9 minus x squared, right? That's the positive half of my semicircle. Okay, so y value is half of my triangle side length. The triangle side length is the whole thing. I can calculate half, so how can I calculate the whole thing? Multiply this by 2. Multiply that by 2. The side of my equilateral triangle is 2 times the height of my semicircle. So we're going to plug that in here for S. S is 2 times square root of 9 minus x squared. That's how we calculate the side length for each of our equilateral triangles. Okay, so half of S is the square root of 9 minus x squared. Okay, that's the height of each of your semicircles. So the whole entire side is 2 of those. And it goes from -3 to 3, and we're integrating with respect to x. So this is the last one. It wants us to find it with respect to y, right? So we have our equation. It's y equals x squared, but with respect to y, we need to solve that equation for x so that we can plug it in. Okay, so it's horizontal, right? We have horizontally, and it's a square. So the area of a square is side squared. Okay, so the side length is the distance in between our curves, which is 2 minus whatever y value we have right there. And that's how we're going to figure that out. Okay? Okay. We'll see you on the next video. Practice these. They're tricky.